Hello students, in this video we are going to be talking about bonding theories, hybridization, and sigma and pi bonds. So there are a couple bonding theories. The simplest is valence bond theory, and this uses the available orbitals of those outer higher energy valence electrons. So for example, if I combine an H and an F, my outer unpaired electron for a hydrogen is a 1s, and for a fluorine, it's in a 2p. So this is why it's important for you guys to know the shapes, because an S is spherical here, and a P has these two lobes, and you can see the best way for them to overlap is head-to-head shown here. So this is going to create your sigma bond. You can also do this with two halogens, such as two Fs, and this overlap here, the overlap representing electron density, the shared electrons or that electron pair, this is your bond, your FF bond. The next type of orbital theory is basically a theory to explain why certain molecules are symmetric. And this is called hybrid orbital theory. We can take methane here, CH4, and note that experimentally, this is a tetrahedral molecule, perfectly symmetric. But how is that even possible when the outer electrons of carbon come from a 2s and two 2p orbitals? The way that we explain that is we mix them or hybridize them to form three of the same type. So you mix an S and three Ps to form four new sp3s. You can see this visually here, the spherical and then the p orbitals blending to form these new sp3 orbitals, and these arrange in a tetrahedral fashion around a carbon center. So that definitely explains the symmetry involved in forming methane. And what I just want to mention is that these are lobes, again, that hold electron density, or the electrons that are involved in bonding can go into them. When you overlap, say, with another hydrogen here, a sphere, an S, it's that overlap that I showed on a previous slide that creates the bond. So it's kind of like a house or a room in a house for electrons. There's a lot of verbiage here, but what I want you to know is on this slide, the hybrid orbital type, whether it's sp, sp2, sp3, is related to the orbital geometry or electron arrangement, or simply just the number of electronic groups around the atom. For example, in the previous slide, we had 4 H's around carbon, 4 groups gives tetrahedral, so it must be sp3. Water has 4 groups directly attached to the oxygen. 2 lone pairs. Notice that a lone pair is a group because a lone pair is 2 electrons and takes up space, similar to a covalent bond. 2 lone pairs and 2 H's, 4 groups will arrange in an electronic fashion in a tetrahedral arrangement, giving an sp3 orbital hybridization. So the bottom line is oxygen, because it has 4 groups, is sp3 hybridized. If you want to name the shape, you just look at the atoms and that's bent. Okay, that's all that you really need to know on this slide. You could just memorize this. If you have a linear arrangement, 2 groups, you have sp hybridization, 3 groups giving trigonal planar is sp2, tetrahedral sp3. Here is just a kind of overview of what I just said. If you take acetylene, for example, something that's disubstituted and linear, the X is your central atom, you have something sp hybridized. So this carbon has a carbon attached and a hydrogen attached, nothing else. So this carbon is sp hybridized. If I look at the left carbon here, it's also sp hybridized. In ethylene, you have a carbon with three groups. You have hydrogen, hydrogen, and carbon. If we focus on this left carbon, this tri-substituted trigonal planar is sp2 hybridized. This right carbon as well, sp2 hybridized. Anything tetrahedral, sp3 hybridized. Sigma and pi bonds. Sigma, these are single bonds. The first bond you have to have. An overlap of an S or P or hybrid orbitals. You need this direct head-to-head overlap for the electrons to share those electrons. A pi bond occurs when you're looking at multiple bonds. It's the second or third bond in a double or triple bond. So you have an overlap of p orbitals. So these are not hybrid. These are just the pure p orbitals. Here, let's say this is the z-axis. So we have two pz's overlapping. You see the shading above and below the nodal plane? That's still one pi bond. That would be, say, the second bond of a double bond. Sometimes these can be hard to draw, so sometimes they're drawn this way, which is shading above and below. But either way, this represents one pi bond. I'm going to go through three examples. So the first is sp3 hybridization of ethane, shown here. So you have a tetrahedral arrangement. You have free rotation around the CC single bond, meaning think of this as like rotors. This sort of understanding of geometry is going to become important because when we start running reactions or looking at reactions, there's a lot of importance on the shape of a molecule and also the resulting products that come out of it based on the arrangement of atoms. Here I just use dashes and wedges to show in 3D. Here I'm showing the orbitals used. So this is the sp3 hybrid orbital. So I show these lobes in yellow. I have the overlap for the CC sigma bond and the overlap for the carbon hydrogen sigma bonds as well, all throughout. When you go to ethylene, you get sp2 hybridized carbons because you have this trigonal planar arrangement here on each of those carbons. And so roughly 120 degrees apart. There is no rotation around this carbon-carbon bond. This is really important because this makes these structures basically flat and fixed. You would have to break the pi bond to allow it to rotate. That means if you have different atoms around the molecule, for example, if I had a chlorine here and above here, that's different than a molecule with a chlorine here and in the lower right. So let's show this. This gray bond is just showing the CC sigma bond, but above and below I have my pi bond. And again, two shading areas, but it's a single pi bond. That second bond of the double bond. Acetylene is a good example of a triply bonded organic compound. This is all linear throughout. There's no rotation here around the carbon-carbon bond, but the whole molecule is rotating, moving around in space and whatnot. Here, and don't gloss over this, don't shy away from the structure because it's important. This gray bond here is a sigma bond. It's an overlap of the two sp orbitals from each carbon. So it used an S and it used a P. Remember that carbon's outer electrons come from an S and you can use 3 Ps. So it has two other Ps that it'll use for pi bonds. Let's call this a PZ. The blue ones can form one pi bond, which is the second of this triple bond. And the yellows, let's call those the PYs. And so that can overlap. Some dotted lines are showing the shading and form the third pi bond here. The other p orbital was used in hybridization to form the sp orbital used for the sigma bond. Okay, let's talk about the effects of hybridization on bond strength. These aspects are gonna come into play in the acid-base section of this course and explain reactivity. So first of all, a triple bond stronger than a double and a single. That might be obvious to you. I can show the numbers here. A triply bonded CC, 965 kilojoules per mole. It goes lower as you go to double and single. Why? Because there are just more electrons holding them together. Think of it as like 3 ropes or 3 cables versus 1 cable holding atoms together. The other thing that I want you to think about is carbon-hydrogen bonds. So when we have acetylene CH versus the CH in ethylene, the doubly bonded guy, the sp2 guy versus sp3, you go from a stronger bond in the triply bonded sp hybridized to weaker bonds in the sp3. Why is that? You can have a think about this, pause it if you want to. And it may not be quite obvious, but what's the difference? The biggest difference is the hybridization. One is an sp, then you have more p's as you go from ethylene to ethane. So the acetylene has more what we call S character. It's 50% S, 50% P, 1 S, 1 P. Here in the tetrahedral, it's 25% S because just 1 out of 4, and 3 P's will be 75% P. Why is that important? Think about the shape of the S. It's a sphere. That sphere can get closer to the nucleus. When you have those p orbitals, you have that nodal plane in the center. So most of that electron density is away from the nucleus. The closer electrons can get to the nucleus, the more of the positive charge they feel from that nucleus. So it's held on tighter. So that explains why these guys are stronger. And what you also find is that's related to length. The shorter, the stronger. You'll find that the stronger ones are shorter than the longer ones. Okay, let's just practice. You guys are gonna answer these questions, so pause this and write your answers down, and then I'll go over it. So first, identify the hybridization of each carbon and nitrogen in the acetonitrile molecule. So you wanna look at how many groups. This carbon has 4 groups, 3 H's and a C, so this is sp3. This carbon only is bonded to a carbon and nitrogen, so linear arrangement, so sp. This nitrogen has a carbon and a lone pair, sp. Notice it doesn't matter if it's a single or triple bond because those don't take up those orbitals. What is involved, because those other guys are in p orbitals. So you're just looking at the carbon, the atom attached or a lone pair attached. Go through, check your answers here. Basically anything with 4 groups is sp3. Again, this nitrogen, 3 bonds and a lone pair. This oxygen, 2 bonds, 2 lone pairs. Anything with 3 groups is sp2, shown here, here, and here. And then the rest are sp2 groups. I want to cover what's called molecular orbital theory, which you may or may not have had in Chem 150 or Chem 160 or your general chemistry courses you've taken. So this is different. This actually explains the bonding in molecules. We just went over hybrid orbital theory. It says that you can combine atomic orbitals of the same atom to produce hybrid orbitals like sp, sp2, etc. Molecular orbital theory is different because you're combining atomic orbitals of different atoms. For example, one hydrogen and another hydrogen to produce molecular orbitals to form those actual covalent bonds. We call these sigma, sigma star, pi, and pi star. This describes covalent bonding. Let's just remember S and P's are the most important. There is a phase associated with each lobe. I can either shade it or write plus or minus. These aren't charges. These are just saying that lobes, for example, 2 lobes with opposite signs for the p orbitals, these, these can combine in different ways where 2 positives or 2 negatives can combine to make something constructive or bonding. Or you can have a plus and minus not combine, and that's destructive or antibonding. So I'll show that in a diagram here. If I take a s orbital from two different h's, I can combine them, and you could think of that just like mathematically combining something. And I can have them overlap and form my sigma bond. Awesome, great. If you combine them that way in an additive fashion, you also have to do it where instead of this HS adds this other S to form the sigma bond, you would have an S minus another S. And that creates that opposite sign that I was mentioning, where these do not form anything constructive, they form something deconstructive, and that is something we call sigma star or anti-bonding. Okay, the reason why this is important is you're going to use the electrons to fill in, just like you do with normal atomic orbitals, fill in the lower energy one first and form this hydrogen molecule. So you just made the hydrogen molecule. If you added two extra hydrogens, like say the H2 minus anion, those two electrons would have to go up top here. That would negate the whole thing. That molecule should not exist. So the whole point is electrons in the pi, I'm sorry, not the pi, the sigma bonding orbital is going to create your bond. Anything in the anti-bonding orbital, sigma star, destroys part of that. You can do this in pi bonds as well. You can have two p orbitals combined and you have your nice overlap forming your pi orbital. That can also create the possibility of a pi star anti-bonding. So you want your electrons in the pi bond, bonding orbital shown here. So I don't have you guys actually fill these up, but I do need you to understand that there are these molecular orbitals that are involved in reactivity. And the reason is that's going to help you predict some reactivity further down the line in the course. So this is just another way to show both the sigma and the pi. And when you combine them, you can see that here. Sometimes people like to show that with just the p orbitals as the pi bond. This is my last slide in this video. Orbitals must have good overlap. So this will come into play later, but these are all examples of good overlap, head-to-head overlap here. Notice the phases need to be the same. This is orthogonal, so these do not have good overlap. Okay, I'm going to end here and I will talk to you guys later.